Hello there, a very good evening to you all. I'm Alan Willison and it's my pleasure to welcome you to this meeting of the Hertford Astronomy Group. Special welcome to everybody there on Zoom. It's lovely to see you as well. We hope you're going to enjoy yourselves. Could we ask you just make sure you keep your fingers away from the space bar, otherwise we might get some strange sounds joining in. Now, we've got a slightly different programme to our normal one because we've got our AGM first, and I know how much everybody loves AGMs. And those of you on Zoom, I think if you look at the title of the broadcast, you've even got it twice, somebody pointed out to me. Those of you here, you can look that up when you get home. Okay, so I'm going to get straight on to this. And we're going to begin with any apologies for absence.
I'm not here.
Okay. Right. By the way, those of you on Zoom, if you want to chip in any direction, just put it in the chat line and we'll make sure all the messages get through. Okay, so the minutes of last year's meeting have been circulated, or rather the links to them were. I hope you've read them all through. Those of you who were at the meeting, do you agree that it was the meeting you attended and that we can sign them off as accurate and correct? Yeah. Okay, yeah, we've got a couple that agreed to that. Any matters arising from those meetings? No. Sorry, from those minutes? Okay, we're doing very well so far. And that brings us to the Chairman's report. Now, the Chairman's report does cover several aspects of the club, so I'm going to read it because I don't want to miss any of the parts out. There will be an opportunity at the end of it if you want to ask any questions. So, Chairman's report 2025. Gives me great pleasure to present to you the 17th AGM of the Hertford Astronomy Group. The club continues to flourish and grow in both numbers of members and events in which we are participating. We have had a very full year of talks and activities in a variety of locations around the county. The Society's main activities are, of course, these monthly meetings, held on the second Wednesday of each month from September to June. As I said, we've taken part in quite a lot of different events over the year. The meetings here, our astrophotography group, HAGOBS, our visual observing group, and attendance at the Bayfordbury Open Evenings, as well as other outreach events, but more about those later on. With regard to the programme, this has been very successful. The evidence being that we have around about 70 people or so at our monthly meetings. We naturally assume that this has been down to our visiting speakers who have covered a range of topics on astronomy and space exploration. We thank Jerry for arranging such interesting selection of speakers. We must also thank Martin and John for their contributions about the night sky which normally start our meetings off. We continue to hold our meetings live and on Zoom for those unable to attend in person, and I must thank Steve and Dan for taking on the challenges which constantly evolve but never defeat them. Also thanks to Steve for editing and the recordings of the meetings that are then transferred to YouTube for later viewing, always with the permission of the speakers. HAGAS, our astrophotography section, that's continued to thrive with our monthly meetings held here at the university. There are often visiting speakers interspersed with open meetings for members to share their experiences. So our thanks to Dennis and Kevin for managing that group. The latest venture, inaugurated this year, has been our visual observation group, known as HAGOBS. Meetings are called at short notice due to the need to respond to weather conditions, and the group assemble at the village hall in Bramfield. Congratulations to Richard and to Alana for organising these events. We have attended the Bayfordbury Open Evenings with indoor displays and outdoor demonstrations. The virtual reality setup is definitely one of the most popular attractions indoors, and Richard's artificial planets keep the interest alive outside when the clouds obscure the real ones. Our thanks are due to all the members who come along to these events, and also to Bayfordbury for inviting us to attend. Outreach events include the Hertford Dark Sky event, where the floodlights around Hertford Castle are extinguished to enhance the views of the night sky. HAG set up an indoor visual display and outdoor visual opportunities for the public who thoroughly enjoy them. Another new event was the talk to the U3A group in Wheathampstead, which is considering the formation of a science group on the back of that visit. Another enjoyable event held in the castle grounds was the observing of the partial solar eclipse in March. We were fortunate with the weather and we were able to view the eclipse with solar glasses, solar telescopes, and a variety of other methods of safely viewing the sun. Again, we thank all the volunteers who came along to that. We visited Bengio School for their annual astronomy evening and provided indoor and outdoor support on another cloudy evening. We also visited Wheathampstead Village Day last July, and we were able to share our interest in astronomy with a fair number of people, even though it was rather cold and wet. Each of those events was well supported by members of the club, and we are very grateful for that support. Membership numbers have been holding up with over 130 full-time members and a substantial number of student and junior members. Tony has continued his sterling work in managing the numbers of attendees. We continue to use TicketSource as a payment platform for visitors. It is vital that we participate in public events to make our presence known so that natural wastage can be replaced with new interest. The report from our equipment officer says that more than any previous year, we've seen equipment being borrowed and used. Really pleased about that. We were donated a 10-inch Meade telescope last summer, and after a bit of tinkering by Richard, it's being well used for astrophotography. Our 8-inch Meade light switch telescope has made several appearances at open evenings, outreach and HAG-OBS events. Our Celestron Mac 127 Go-To setup has been out to one of the university students, as well as a younger student who lives in Wing, Buckinghamshire. Apparently, we were the nearest club to her who were willing to loan a telescope for a school project. We are now looking at spending some of the funds that we've accumulated on getting a ZWO C-Star Smart APO telescope for HAG. It's exceptionally portable and would be most suitable for our outreach events, as the faint fuzzies that can't be viewed via an eyepiece can be live stacked and viewed on a screen. With a tripod, it would cost around £500. As you know, this has been very much a wait and see thing, but our equipment officer has seen some truly remarkable captures from both the S50 and the smaller S30. Don't worry, there won't be a test on those numbers. ZWO are bringing out a new S30 Pro later this year, which has a new, better quality integrated camera and an EQ bracket mount for the tripod. This is the one that we should possibly consider after having seen trusted reviews on YouTube. It was exhibited at the NEAF in the US, but think it will be released here in the autumn. Does anybody have any objections to us spending the money on that? Speak now or forever hold your peace. Zoom, put your hand up if you object.
No.
Nobody. Okay. You see Steve smiling from ear to ear. Okay, finances are well tended by our treasurer, Anne Godwin, who will have her own star spot in a moment, so I won't say any more about that. Administration, Alana Smith is our secretary to our group. Alana, unfortunately, can't be here tonight. I believe she's in Florida. Poor soul. Alana prepares agendas and minutes for our committee members and distributes these as necessary. Alana also deals with any other correspondence that is not covered elsewhere. We are indebted to her for keeping us on the right track throughout the year. Other committee members, Leon Gvertz, Dennis O'Shea, Danny Emmett, they must be mentioned for their attendance at so many events. They offer support to the many events taking part throughout the year, as well as offering huge amounts of common sense to the committee meetings held throughout the year. We mentioned earlier John Fraser's contribution to our monthly meetings. We must thank and also express our thanks to ex-committee member Terry Creasy, who continues to supply us with monthly night sky tours, which are published on the website. And Terry also attends some of our outreach events. We've been pleased to be able to hold our meetings here at the university. They let us use this lecture theatre for our monthly meeting and also make a meeting room available for our Haggas meetings at no charge to us. We're very grateful to the university, and in particular to Ben Birmingham's team at Bayfordbury for their continued support. Finally, members. We must thank you, the membership, all of you. Without your support, the club would not exist. Your attendance at meetings and outside events is very much appreciated, and the fact that our numbers are so strong can hopefully be interpreted as that we are doing something right. That concludes my report. Thank you, you're very kind. Do we have any questions? Okay then, if there are no questions, we will move on to the statement of accounts. So over to you, Anne.
Hello, I'm Anne. You won't have seen me much in the last couple of years because I've been attending on Zoom. Hello, fellow Zoomers. But I have actually I was a founder member along with Alan 20 years ago. So we have been around the block a few times. So this is my report for the accounts period 1st of April 2024 to 31st of March 2025. There we go. I'll go off. Now, you might be able to see if you've got binoculars. I trust some of you do. So, first of all, they're very simple, the accounts. So I'll just go through income. So first of all, membership subscriptions. So at the AGM in May 2024, the membership agreed to keep the annual membership fee at £10 pro rata, as our income balanced with our spending over the financial year, and we continued to end the year with a healthy balance last year of just over £4,500. Now, we know that's a really low subscription payment, and we wanted to see how that would go over a couple of years and see if we started to need to increase the subscription. But you'll see what my conclusion is at the end of this year. So over the year, we had 135 people joining and paying as members this year, generating an income of £1,293.50, which is around 30 more people than this time last year. 91 people joined at or before the first meeting of the new programme year, which is in September, with the rest joining in small numbers each month since then. Visitors, we charge £2 for visitors and plus a 30p fee for Zoom users. And we continue to use Ticket Source, as Alan has already described, which is the online platform, in exchange for a fee. Visitor numbers are irregular, with between 11 visitors and 2 visitors, a decrease on last year, but yields £110. But it wasn't much more last year. In terms of expenditure, first of all, banking. We bank with HSBC, and they introduced an account fee a few years ago after offering free banking to us for many years. And that account fee is at least £5 per month. It depends on how many transactions go through. And we paid £61.20 of charges over the year, which is similar to last year. Looking at IT expenses, we continue to pay a web hosting fee. This year, this increased to £107.86, up around £20 on the year. And we also have a domain name fee of £10.79. We also invested in some better IT equipment to support delivery of our in-person monthly meetings here. So new mics, costing £199.99, and a new scanner at the door costing £45.99. And we continue to meet in person as well as on Zoom, and are fortunate, as Alan said, that the University of Hertfordshire venue is given to us free, so there are no ongoing costs. Up until a few years ago when we moved here, obviously our biggest expenses were the venue fees, which were quite substantial, which is why we did pay a significantly higher membership fee at that point. Speakers. As always, we've enjoyed a varied programme of speakers, some of whom charge a speaker fee, some who just ask us for their expenses, and some who provide their services for free. We paid a total of £301.25 in speaker fees this year, which was down around £83 on the year before. And it is our tradition to offer our speakers some refreshments, as many have travelled some distance or come straight from work, and this cost around £120.73 this year in meals. On to the Federation of Astronomical Societies that we belong to. We maintained our membership of FAS once more at a cost of £30, a charge which hasn't changed for many years. I don't know how they managed to keep it that low, but it's always been that since we joined, I think. And they offer a useful publicity service, as well as other generally useful information that we access, and a newsletter. We also took out public liability insurance with the FAS at greatly reduced fees to if we went directly to a broker. And in this last year, we paid 2 years' worth of insurance at a combined cost of £108, as the fee for last year was not included in last year's accounts, so we've paid double this year. Moving on to advertising and promotion. Our annual recruitment drive at the Howard Centre in Welwyn Garden City last year cost £78. They'd suddenly put quite a high fee on it, and we're not intending this year to repeat that. We're looking at other venues for where there is no charge, rather than paying that quite steep fee. And other expenses. So Jerry provided refreshments at the March 2024 My Telescope even doesn't work sessions at a cost of £14.50, and Alan provided mulled wine and other goodies at the December meeting at a cost of £63.78. Tony bought new lanyards at a cost of £189.68. And other sundry expenses included printing paper, ink, stamps, etc., at a cost of £90 and 2p, and an unfair parking ticket, aren't they always, costing £60 for a volunteer at one of our events that we decided to pay. And they're always unfair. So looking at our closing balance, we began the year with a balance of £4,629.41, and we end this period of accounts with a balance of £4,551.12, which is a decrease of £78.29 over the year. Auditor, I extend my grateful thanks to Simon Poley, who has audited 2 years' worth of accounts, and he has graciously agreed to act as auditor next year, so I shan't be asking for an auditor from the membership here today. So you've avoided that one. And then moving on to subscriptions for the next year coming up. As we have maintained our balance and we are sitting on £4,500, which hasn't been doing a lot the last couple of years or the last few years, your committee would like to recommend that we maintain the reduced annual membership fee of £10 pro rata for adults 18 years of age and older for the next year, but that we may look at increasing that in a year's time. Looking at our proposed expenditure for the next year, so your committee would like your approval to make the following purchases in the next financial year, as the balance in our account is higher than necessary and we can afford to invest in items that will aid our outreach significantly. First of all was the smart telescope that you've just heard about with equatorial wedge, whatever that is, at a cost of around £600. Then an iPad to mirrorcast the images, which is around £450. We'd also like to invest in another couple of headsets for the virtual reality that goes down a storm at any of the outreach we do, and we'll reduce the queues that we always get at those events from particularly the youngsters. And another 2 Meta headsets would cost around £700 with all the bits and bobs that go with it. And then we'd also like to upgrade our display boards, which are looking a little worse for wear. I haven't got a cost for that, but it will be a couple of £100. And also, the last thing on the shopping list is new high-vis jackets, because the ones we've got are falling apart now, and we really want to make a good impression everywhere we go. And again, that would probably be a couple of £100, if that. So all of those costs come to, if we were to go ahead and get all of that in this next financial year, that would bring us up to around about £2,000 worth of expenditure, which would bring our operating balance down to £2,500, assuming that we get similar membership going forward that we've had and enjoyed this last year. So, 2 questions. Any questions from you about any of that, and also comments on the expenditure?
I should just mention there will be one small additional charge, which is for the eclipse glasses. I gave the society 150, and at the end of the event we only had 15 left, which shows how successful
15.
it was. 15, 1 5,
Wow.
yes.
Yeah, that's amazing. So that was a good purchase then, Jerry.
Yeah.
Any other questions generally about the accounts? There never is, really, are there? But glad that there are no questions. And any, shall I just put it to a vote about the suggested expenditure? Are people happy with us, or your committee making decisions? We may not actually make all those purchases this year, but those are things on our mind at the moment that we think would enhance particularly our outreach work. So what do we do? Do we do a vote?
Yeah, hand up in favour.
All votes, all hands in favour, say aye. Aye. Lovely. Thank you very much.
Okay. Thank you very much indeed, Anne, for your report. The next item on the agenda is the Honorary Auditor's Report, which has come in by email. Alan, as per Anne's request, this is just to confirm I have checked the accounts and the paperwork and bank statements for 2024 and 2025 and found everything to be in order and absolutely tickety-boo. Have a good meeting tonight. Sorry I can't be there. Kind regards, Simon. If you've got any questions about that, see us after and you can send them to Simon. Okay, so brings us to the appointment of officers and members of the Management Committee 2025-2026. Your current team are willing to continue their roles here. Do we have any other nominations either from the floor or from Zoom? Okay. In which case, what I'm going to suggest is that we can vote all the regular people who've offered en bloc onto the committee. Could we have a proposer for that? Can we record that? Okay, and can we have a seconder? Okay, fabulous. Write it down. And I suppose we should ask for a vote for it. Hands up in favour of those people standing. Any objections? Just you dare. Tony's been trying to get off the committee for a long time and we won't let him. So thank you very much indeed for that vote of confidence. The appointment of the Honorary Auditor, item number 8 on the agenda. We heard from Anne's report that Simon is willing to do it, unless, of course, there's a contest for the job. Okay, Simon, the job's yours. I don't think we need to vote on that one. Brings us to any other business. Is there anything anyone would like to raise? My goodness, that's great. Okay, in which case we will then move on to the rest of the evening's events. And Leon?
I'd just like to...
That's very kind of you, Leon, and very much appreciated. I do enjoy it. Okay, so that brings us to tonight's star event, our speaker, and I'm going to ask Jerry to introduce Alan.
Thank you very much. Well, for this month we have a unique event. For the first time in our history, I think, we have a Professor of Astrostatistics. Alan Heavens has been involved with the University of Edinburgh for many years, so it's very good that we're able to get him all the way down here in Hertfordshire. It's a very interesting subject. And it's down to the fact that when we look at things in the sky, they are not always where they appear to be. And this is one of the effects, or one of the unexpected effects that came out of Einstein's theory of relativity, or perhaps we should say Einstein's theory of gravity. I'd like you to welcome Alan Heavens, who's going to tell us all about it.
Okay, well, thank you for the invitation to come and speak. It's a great pleasure to be here. I'm going to talk about light bending in the sky, and as Jerry said, it's one of the predictions of, or one of the features of Einstein's theory of relativity, that what you see in the sky is not quite what is there. And if you look at any distant object, its position is slightly wrong, its shape is slightly wrong, the image is imperfect. And I'm not talking about the optics of the telescope distorting things or the atmosphere. It is, as Jerry says, gravity, that light gets bent on its way from the object into your eye or into your telescope. And that imperfect view of the universe You might think it's a nuisance, and in some circumstances it is, but that distortion pattern contains a lot of information which we can use to tell us about the cosmos. So I'm going to talk to you about how we use it to tell us about what the universe is made out of, what its future is going to be, and I'll just touch on the statistics that we use, because it's very much something that we need quite fancy statistics in order to decode what is in that pattern. So before I talk about that, let's just give it a bit of context. So I'm going to be talking about cosmology, so the universe on the largest scales, and for the last 100 years or so, 110 years, we've known some strange things about the universe. Starting with this chap. Does anybody know who this is? Any guesses? He was the first to provide evidence that the universe is expanding. Schwarzschild? No, it's actually Vesto Slipher. So very often the discovery of the expansion of the universe is credited to Edwin Hubble, but if you look at the historical record, then the first measurements showing the recession speeds of nearby galaxies was due to Slipher. So this is you'll notice here that these speeds, which are in the second column, are predominantly positive, which means that these galaxies are moving away from us, and one or two of them are moving towards us. But we understand now why that is. But this was the first evidence that galaxies were predominantly moving away from us, and the first evidence that the universe was expanding. So, and we can see some early photographs here of the spectra of some of these galaxies. Some of these you'll recognize. And if you take a spectrum of this object, there's a couple of absorption lines here due to calcium, which you can probably make out here. These two dark lines, the H and K lines of calcium. And you'll notice that they appear here. If this was a color sensitive plate, then this would be the blue end of the spectrum, and this would be the red end of the spectrum. And you'll notice that as we go down the slide, then these two lines here get moved further and further to the right. And this is essentially just the Doppler effect applied to light. These galaxies are moving, and the faster they're moving, then the further the light gets shifted towards the red end, the so-called redshift of the galaxies. And if you look down here, you'll see that the one at the top is big, appears big, and they get smaller as you go down, and that's because they're further away. So what this encompasses is a law which is due to Hubble, which is that the recession speed is given by a constant times the distance. The further away you are, the faster the recession speed, and the constant of proportionality is called Hubble's constant, and it amounts to about 70 kilometers per second for every megaparsec away the galaxy is. So it sounds a bit strange. I mean, why is it that everything is moving away from us? It seems to imply that we're at the center of the universe, but it doesn't. And I can illustrate that with this picture here, which is mostly stars. What's really happening as the universe expands is that everything gets further apart from everything else. So if I were to take this picture but a little bit later, then it would look like this. So I've superposed the two pictures. One is I've just basically changed the zoom setting, and I've matched the two pictures so that they agree here. So if you imagine that this is us, I mean, these are stars, and actually the expansion of the universe doesn't really apply in the simple way to stars, but if you imagine that these are galaxies rather than stars, then if we're sitting here, then the pattern is of a recession speed which is proportional to distance. And you can see that, for example, here, this star, or this object has moved from here to here between the two pictures being taken whereas this one over here, which is further away, has moved from here to here. And it's fairly easy to convince yourself that the distance that's been moved in that time period between the pictures is proportional to the distance away from us. So if we're sitting here, then it looks as though everything is moving away from us. It might be worried that we had some body odor or something that caused them to move away. But actually I can do this exercise and center it on any other position in the sky. So here I've done exactly the same thing. I've taken the two photographs. One is slightly bigger than the other, but I've matched them up at this point here. So imagine that you were in the universe at this point. You would see exactly the same thing, that the objects which are quite close don't move very far, so their speed is slow, whereas objects like this is what was our original position, then this object will have moved from here to here. So this observer here would see exactly the same Hubble law as we do. So there's no particular center of the universe. Everywhere would see the same thing. And here's another illustration. See if this works. To give you a feeling in 3 dimensions of what's going on. So if you can imagine, it looks a bit weird from here. Yeah, so you can see this sort of grid of lines and the galaxies moving apart. Basically, everything is moving away from everything else, and it's very much like just changing the zoom setting on your camera. So that's the picture that we have of the expanding universe, and it was something which was a slight embarrassment to Einstein because he'd been working on his theory of gravity. And he came up with a very nice, elegant theory of gravity, General Relativity, which he then changed. He added in an extra term into his equations by including the cosmological constant. And the reason that he did that was that his equations without this extra term do not allow for a static universe. The universe has to be either expanding or contracting. And so he, at the time, was thinking that that the universe was static and it existed forever. So he had to include some extra term in his equations of gravity, which tends to pull things together, to include an extra term that pushes, that precisely balanced the attraction of ordinary of gravity as we know it. So this is these are his equations. With some constants simplified just for illustration. His original equation of general relativity didn't have this extra term. Now, I'm not going to explain too much about what the equation is. This tells you something about the curvature of space-time. This tells you something about this is dependent on the contents of the universe. And I'm sure you'll agree that without this term, this would be an extremely elegant theory with just G equals T, basically. And it's slightly uglier, not much, but slightly uglier with this extra term. So this is the cosmological constant. It's debatable whether he described it as his biggest blunder or not, but there's some evidence that he did. But I think he really missed a trick, because if he'd stuck to his guns and not included this term, he would have been able to make a prediction that the universe could not be static and it must be either expanding or contracting. And I think you'll probably agree that if he'd been able to make that statement, then he would probably have been famous today, and you'd probably recognize this picture of him as a famous person. Okay, so let's just have a look at the consequences of having an expanding universe. So let's start by running time backwards. So let's say we're here, all the galaxies have velocities which are moving away from us. If we run time backwards, then these galaxies in the past would have been closer together. And if you extrapolate far enough, then you find that at a certain point in the past, then the galaxies are all sitting on top of each other. And that time, from the expansion rate that we know, that time is about 13.8 billion years ago. So the consequence of the expansion of the universe is that there appears to have been an event that took place 13.8 billion years ago, that sent the constituents of the universe moving apart at high speed. And that event is, as you know, called the Big Bang. So that's quite an extrapolation, just from saying the universe, things are moving apart, to say that there was an event that started the universe is quite an extrapolation. But there's plenty of other evidence that tells us that that this event actually happened. One of which was in the 1960s, when the light that was left over from the Big Bang was detected by accident by Arno Penzias on the right there, and Robert Wilson on the left. I'm always intrigued because these pictures of these two, Penzias is always much taller than poor Robert Wilson. And I have a suspicion that Penzias insists on being closer to the camera so that he appears bigger. I think I've yet to find a picture where they're the other way around, even though actually Robert Wilson was quite tall. Anyway, I speculate. So this is so they discovered this light by accident. They were using this radio antenna here to detect radio waves from the galaxy. And what they discovered was that there was an extra little hiss which was coming into the telescope that they didn't really understand the origin of. At some point they thought it was due to some pigeon droppings, famously, and they removed the pigeon droppings, and I understand also removed the pigeons, but the hiss was still there, and it turned out that what they had detected was the radiation left over from the Big Bang. And this is where they published it. It's one of the most famous pictures, one of the most famous papers in astronomy. It's actually hidden by, thank you. And it goes by the exciting title of A Measurement of Excess Antenna Temperature at 4,080 megacycles per second. Now, I'm sure that if you were reading the journal papers, you would see this title and think, oh, I must read this. This is going to be really exciting. So they were very cautious about the interpretation of this, and just simply reported it as just an excess signal that in the telescope. There's a sentence at the end which says a possible explanation for this is in the companion paper, which is the end of which you see here, which is signed by Bob Dickey, Jim Peebles, Roland Wilkinson, where they were basically scooped by these guys because they were actually building a telescope to search for this signal. And they were scooped by Penzias and Wilson, who found it by accident. So I've sort of quizzed Jim Peebles about this over beers at some point to see what their reaction was, but he's a very gentlemanly person and was extremely polite, but I could tell that they were mightily cheesed off. So, what do we know from this light that's left over from the Big Bang? Well, one of the things which is quite profound is that the light has a almost perfect black body spectrum. It's the best black body that there is that we have in the universe. It follows exactly the Planck law. Here are the measurements from. This is the Cosmic Background Explorer, which was launched, I think, in 1990, and within the first 9 minutes it had measured the spectrum, and after that it also did many other things, but within the first 9 minutes it had this spectrum, and the measurements are given by these points with the error bars, and they fit this line perfectly well, especially when you recognize that these error bars are not the usual 1 sigma error bars. There are 400 sigma error bars, so the errors on these are actually 400 times smaller than the lengths of the line here. It's astonishingly accurate black body. So the interpretation of this is quite profound because at the moment the universe is so tenuous, it's so empty, that if you have some photons of light, as these are, they will not thermalize. So you get this black body spectrum if you have many, many interactions between the photons and matter, and it will settle down into this black body spectrum. If you put some radiation into the universe today, it will not get to this black body spectrum because there aren't enough collisions. The universe is too empty. So what this is telling us is that in the past, the universe must have been much denser than it is today. So this is also evidence that the universe went through a very dense phase at some point during the past. So another thing that COBE did, the Cosmic Background Explorer did, was to look at the fluctuations in temperature. So the radiation is now at a temperature of about 2.7 Kelvin, but it fluctuates by a tiny amount, by about 1 part in 100,000 across the sky. So it for the first time measured these fluctuations, and these fluctuations are important because if the universe were entirely uniform, then no structures would form. But these small fluctuations of 1 part in 100,000 give rise to all the structures that we see today: galaxies, clusters of galaxies, stars, planets, and so on. They all come from the gravitational instability of these fluctuations. So if the universe is not quite uniform, if there are parts of the universe which are slightly denser than average, they have a slightly stronger pull of gravity, so they will pull more matter in, and they will get denser and denser. So it's an unstable situation. Any overdense regions get progressively more overdense. So this was an absolutely groundbreaking discovery. It was published in the usual journals. This is the Sun. It was quite controversial at the time because the technology was not great. So the detectors were very noisy. So part of the fluctuations that you see here are fluctuations in the microwave background temperature. Part of it is just random noise in the detectors. And so there was some discussion at the time about whether COBE had actually discovered fluctuations in the microwave background, or was it all noise? So this is one place where you can use statistics to tell you, and I'm going to use you as guinea pigs in this to see whether you can do the statistical analysis in your heads. So here are 4 pictures, simulations of the sort of pictures that COBE was taking. 3 of them are just random noise. 1 of them is random noise plus some fluctuations like the universe has. So your task is to decide which of these is the one which is not completely random noise. So who votes for number 1? Who votes for number 2? Who votes for number 3? And who votes for number 4? Okay, so a handful of number 4s. 2s and 3s were split. Maybe slightly more 3s. The actual answer is number 2. Okay, so some of you can give yourselves a pat on the back. What is it about it? Well, the hot spot, the brightest spot here is quite bright. It's not really the other random ones don't have anything quite as white as this one. Probably you can maybe also convince yourself that the darkest spot is maybe just a bit darker than in here. We would use statistics to quantify this sort of thing, but you can see that many of you have managed to do it without doing any sums. Okay, so what is this? What are these fluctuations? Well, they're basically sound waves, and they evolve with time. As I mentioned, they will collapse. So if you translate those, these are very long wavelength. I mean, really long wavelength fluctuations, basically about the size of the universe at the time. But if you then change their wavelengths a bit so that they are things that we could hear, then it would sound like this. So let me see if I can click on the right invisible part of the screen and see if it will work. Yeah, so here it comes. that's about 1 billion years of evolution of the fluctuations in the microwave background. I'm not sure what it tells you, but it just gives you an idea that that these are sound waves, and that they will evolve as the universe evolves. And as I say, it's a very long wavelength, very, very long wavelength, so that's why I've put this dog with large ears suitably to hear it. So how has this developed over time? Well, the COBE was the first of the experiments to look at the microwave background. This is the most recent all-sky picture taken with the Planck satellite launched by the European Space Agency. What you see is that you get much more fine detail because the detectors had much finer resolution. And this map tells us an enormous amount of information. Again, you need statistics to extract the information out of it. And the way that we do that is to look at the amplitude of the fluctuations on different scales. So this is the whole sky, which has been sort of unwrapped. And what you can see is that there are some fluctuations on small scales, about the size of my thumb here, but you can also see that there are some larger scale fluctuations, larger areas of blue over here, larger areas of red over here. The relative amplitude of the fluctuations on different scales contains an enormous amount of information. Oh yes, I've got a picture of the, maybe you can just, I've got something behind that corner, so thank you. You can, if you have an old television in your loft, then you can make yourself a microwave background telescope. If you take your old TV, analog TV, and don't tune it to a channel, then you get all this noise. The younger members of the audience have probably never seen this, but I can remember this. When the aerial had fallen out the back of the TV, it would look like this. Yes, yes. So about 1 in 100 of the flecks in the that you see there is due to a microwave background photon coming through the detector, getting amplified hugely because the TV has an automatic gain and it's searching for a signal, so it ups the gain as much as it can and can be sensitive enough to calculate to measure some of these things going through. So the way that we look at this statistically is to look at the amplitude of the fluctuations on different scales. So what this diagram shows you, which is one of the most useful diagrams that we have in cosmology, it shows you essentially the amplitude of the fluctuations on different scales, and it's back to front like most astronomy diagrams are. That the large scales are on the left and the small scales are on the right. So this peak here that you see is actually the small scale stuff that you see here, but there are fluctuations on even smaller scales, on the sort of millimeter and centimeter scale on this diagram. And I think this one will show essentially what's being picked up by different parts of this diagram. So as you see, when you go from left to right, then you start off by picking up the large scale features, and then you get the real fine detail is being measured by what's on the right hand side. Now the thing about this graph here is that we can make very good theoretical predictions for what this graph should look like. And the details depend on what the constituents of the universe are, how fast the universe is expanding, and so on, how much ordinary matter there is, and many other things. So by matching the theoretical curve to the data, we can determine the contents of the universe. And the green line that you see going through here is the best fitting theory. And what you see is this spectacular agreement between the data and the theory. So if anybody doubts that the Big Bang happened, then you just need to point them towards this diagram and say, all right, give me another theory that gives you such good agreement between the measurements and theory. So we know a lot about, so we know, for example, the expansion rate of the universe. Well, actually, this is now a little bit controversial. It's about 68 kilometers per second per megaparsec. Various other things, which details I won't go into, but just to simply point out that we know these numbers with typically about 1% errors. Before we had the microwave background measurements, these numbers were perhaps known to a factor of 2, and now we know them to about percent precision. Okay, so one of the things that we know from this diagram, but we knew from earlier observations, is that the universe is not just expanding, but it's actually accelerating in its expansion. And this came from observations of supernovae, particular type 1a supernovae, that probably consist of a white dwarf star which is in a binary system, accreting matter from the companion, and when enough matter gets dumped onto the white dwarf, then it collapses. When it collapses, it also explodes and becomes extremely bright, being typically about 100 million times the brightness of the sun for a week or two. And here's I think a simulation of a bit of the universe where every so often there's a supernova explosion that goes off. So one just happened here. So we can observe these things. Because they're so bright, we can see them a long way away. And because of the finite light travel time, if we see distant objects, we're seeing them at times in the past. And what that allows us to do is to map the expansion history of the universe over time. So we can see how it has been expanding over time. And the real surprise in the late 1990s was that the expansion of the universe was actually accelerating. Now, gravity should slow things down, but that's not what's happening. The expansion rate is actually getting faster. So this was perhaps the first really conclusive evidence that Einstein might have been right, after all, to include his cosmological constant, because with the cosmological constant, then you can explain this acceleration of the universe, and you can also explain the pattern in the microwave background. So, as I say, it was a big surprise, but now it's accepted. But it leaves us with the question of why is the universe accelerating in its expansion? One possible explanation is that the law of gravity, including the cosmological constant, which pushes, that's just it. The extra term that Einstein put into his equations in order to give a static universe, that term can account for the expansion. But we're curious to know whether that's really the answer or whether it's something different. And so one way to reinterpret Einstein's equations is as follows. So Einstein's original equations look like the one at the top. So as I say, this is the left-hand side is to do with the curvature of space-time. The right-hand side is the matter content in the universe. And this is, as it's written, is just a feature of the law of gravity. But nowadays, we don't like this equation very much. But what we do is to take this term over to the right-hand side. So add that term to both sides, and you get the equation at the bottom. So, all right, I've done a tiny piece of mathematics. So what? But the physical interpretation is different, because here this is to do with the matter content of the universe. So what we can do is to in a sense just recreate Einstein's original general relativity equations, which is that the curvature of space-time term is equal to something to do with the matter content. But we have a new constituent of the universe. We interpret this as some extra stuff. Okay, it's extra material of some sort, but it's very weird material if it's on the right-hand side. And this we call dark energy. So when you see references to dark energy, then typically it's basically Einstein's cosmological constant, but reinterpreted as something which causes gravity. And we'd really like to know what this dark energy is. Is it equivalent to Einstein's cosmological constant or not? So one way to, if it is equivalent to Einstein's cosmological constant, then what this corresponds to is an energy of the vacuum, that the vacuum has an energy density associated with it. And that's not too much of an anathema, because we know that the vacuum is not a completely empty space. We know from quantum mechanics that particles can pop into existence and then annihilate very shortly afterwards. So we know that there are things happening in the vacuum. So the notion that the vacuum has energy associated with it is not completely crazy. The trouble is that if you look at the quantum mechanics of it, then this term should probably be something like 120 orders of magnitude larger than it actually is. So the notion of the vacuum energy is not crazy, but the value of it is completely crazy. So particle physicists don't really like the idea of a vacuum energy at this sort of level, because it's very difficult to account for it. So we explore other possibilities. So other possibilities are that that this is not a vacuum energy, but it's a new field. It's new stuff. This is our current understanding. So how much of this stuff do we have? So to fit the microwave background, we need something like only 5% of the energy density in the universe is in a form that we know, sort of standard, atoms, electrons, protons, neutrons, and so on. About 25% of it is in some form of dark matter, which appears to be cold, but we don't know much more about it than that, except that it's dark, it doesn't interact with light. And then the rest of it has to be in this really strange form. Now, this is really, really strange stuff. Dark matter could just be some new form of particle that we haven't discovered in terrestrial experiments yet, but dark energy is seriously weird, because this is something that has an energy. It has a pressure as well, but the pressure is negative. So it's extremely strange material, if that's what it is. And we'd like to know exactly what that is. The microwave background is not a very good way to probe it, so we need some other techniques, and this is where the gravitational bending of light comes in. So the way that Einstein's theory works, it can be expressed in words to say that if you have some matter around, then that curves space, or space-time to be more precise. So Einstein expressed it as saying that matter tells space how to curve, and then once you've got this curved space, then space will tell matter how to move. So if we were to, say, fire a particle or indeed a photon of light into this curved space-time, then it will follow trajectories which are not straight in some sense. It's going to get bent. So we can use this, and in fact it was famously used for the first time in 1919 when Eddington had an experiment to test Einstein's theory of gravity, and by measuring the bending of light during an eclipse. So here is a sketch from the time showing that if you have a star which is almost behind the sun, then the light will get bent by gravity so that it will appear not where it is, but will appear over here at a different angle. And the eclipse is used to block out the light from the sun so that you can see the stars behind. Now, Newton's theory either predicts no bending at all because the light particles are massless, or else you can sort of fudge it to calculate what the bend angle should be. And Newton's theory either gives you 0 or it gives you precisely half of Einstein's value. So it's something which is testable. You can test whether Einstein's theory is favored by the data by measuring this angle. It's a really hard experiment to do because the deflections are really tiny, around about 2 arc seconds for something which is close to, for light that's passed very close to the sun. But the measurements were made, the data were analysed and published again in the usual journals, in this case the New York Times, and light all askew in the heavens, men of science more or less agog, and Einstein's theory was triumphed, and stars not where they seem to be, but nobody need worry. That's a reassuring thing. I'm glad that they did that. So Einstein was very pleased with this result, obviously, favoured his theory, so much so that he wrote a postcard to his mother. Here's a reproduction of it. It says, Liebe Mutter, I'll translate it for you. It says, Dear Mother, but I don't speak German, so that's as much as I can do. But trust me, he was very pleased. Okay, so gravity bends light. You can light that passes close to the sun is bent by a tiny amount. If you have a black hole, then you can have more exciting things. You can even have light that can go round in a circle. So if you wanted to comb your hair, but you didn't have a mirror, then if you had a black hole handy, if you illuminated the back of your head, then the light could go round and then into your eye, so that you could comb your hair without use of a mirror. It's not a facility that he used on this occasion, evidently, but in principle. So we sometimes see very strong, this would be called gravitational lensing. Sometimes we see very strong bending. Here's a cartoon of the sorts of things that we do detect. So here's a galaxy in the background. If there is a large amount of matter that you might have in a cluster of galaxies that might have 10 to the 15 solar masses or up to 10 to the 15 solar masses in a small volume, it can bend the light enough to significantly distort the pictures of the background galaxies. And here's a space telescope image of a cluster of galaxies. And these highly elongated images that you see here, they're just ordinary galaxies in the background, but their light has been stretched out by the bending into these huge arcs. So these are really useful because it can tell us a lot about the mass distribution in clusters. So we know here there's a lot more matter than is accounted for by the matter in the galaxies that you see. So this is also evidence for dark matter on a very large scale. What we concentrate on at Imperial is not these really extreme events where you have an enormous amount of stretching, but just the general small deflections of light that happens because the light has travelled through a lot of the universe, and the universe is clumpy, as we saw. So the light gets bent by a tiny amount, so the image of a galaxy will get slightly distorted as it goes through the universe. And if you look at a sort of typical galaxy, distant galaxy, then it's not going to get stretched out like those long arcs, but its shape will change by about 1 or 2%. But it happens everywhere. So there is a distortion pattern which is difficult to measure. So here, this is a picture of the Hubble Deep Field, and every single galaxy that you see here has a distortion which is roughly 1 or 2%. So we can use that. If we decode that using statistics, we can work out where the mass is, because by looking at the distortion pattern, we can work out what the mass distribution has to be in order to give the slightly distorted picture that you see. And it's a tricky one to do because we don't know if a shape of a galaxy has been changed. If we knew what the shape really was, that would be fine, but we don't. So what we have to do is to do a statistical analysis, which basically looks at, let's say, in one patch of the sky, if all of the galaxies seem to be elongated in the same direction, then there's maybe two possible explanations. One is that they were born that way and they happen to be aligned, or else, perhaps more plausibly, they have random distributions, but they've all been aligned by the bending of light along the way. So if we assume the latter explanation, then we can tell where the matter is. And this is a picture from the dark energy survey that's recently mapped the distribution of matter in just one part of the sky. And you can see the density of matter here. I was going to say dark matter, but it's actually the entirety of matter, dark matter plus the ordinary stuff, since gravity doesn't care what the stuff is made out of. Okay, so how can we use this to tell us about what's causing the acceleration of the universe? Well, we have a couple of possible explanations. One is that it is just Einstein's cosmological constant. It's just a feature of gravity. But if we put the term on the right-hand side, then it's stuff. It's something that looks a bit like vacuum energy, or it might be vacuum energy. And how would we tell the difference? Well, if it's some stuff that evolves with time, then it differs from the effects differ from lambda because the cosmological constant, because the growth rate of structure is different. So when we look at really distant objects, then we're looking at the distortion of the light as it passes through the universe, but we are looking so far back in time that over that time, the time that it takes the photon to get from the source to us, the universe has evolved. Structures have collapsed, and the universe has got more and more clumpy as time's gone on. So looking at really distant objects, we're actually probing how fast the structures have grown over time. And there are subtle differences if it's Einstein's cosmological constant or some new stuff which evolves. There are also some other effects. The geometry of the universe gets messed up as well. So that also helps us to work out what the universe is made out of. The other possibility is that since we know that we can get these effects of acceleration with Einstein's theory, we can also test other gravity theories, and there's a lot of different theories that go beyond Einstein, which have some of the same features that they will cause the acceleration of the universe. So we can test Einstein's theory of gravity as well against other contenders. And if we change the gravity law, then the light bending is going to differ. Also, structures will grow at a different rate because the gravity law is different. So these possibilities lead to very subtle changes in the distortion patterns that we expect, and we can use statistics to distinguish between the two. So this is some of the work that we do at Imperial, where what on the left-hand side, what's represented is the whole sky, which has been unwrapped, where we observe only part of the sky. So this is what the Euclid satellite, which I'll talk about in a moment, will look at. So it will look at a fair fraction of the sky, but it's going to miss out the galactic plane here in the ecliptic. So it gets data from part of the sky. And what we will be able to do is to work out the matter distribution in different parts of the sky. So here, because the measurements the measurements of the distortion pattern are quite noisy, they're imprecise. It means that there's more than one possible distortion map which is consistent with the data that we collect. So we need to consider all possible maps of the universe, all possible distortion maps that are consistent. So what this video shows is all the possible maps that are consistent with the data. If I run it again, what you should see is that where we have data, then the distortion map will be quite stable. It's not going to vary very much. But in the places where we don't have any data, then the allowed distortion is quite variable. So you should see part of the map on the right is stable, and the other parts move around, and it'll match up with the thing on the left. So you can see here in this bit here. Maybe it does it match up, or maybe I've got this thing the wrong way around. no, I think it does match up. So that's one of the things that we do. This involves lots of computation. We're basically trying to determine 10 million numbers at once. So we use supercomputers to do it. Another thing that we can do is to use machine learning techniques to analyze these complex data. And this is my student Lucas, who's just submitted his thesis. And he's shown that you can use machine learning, in this case based on convolutional neural networks, if that means anything to anybody, to extract the information, a lot of information from the data. And you can do better than the traditional ways that people analyze the data. So let me perhaps just say, to give you a flavor of the sorts of things that we do. This is this part here tells us the way to interpret this is that with the old statistics, you can work out the density of the universe here and the properties of the dark energy. And basically it says that the properties of the dark energy and the density of the universe have to live somewhere inside this grey area. So we're a bit uncertain, in particular, about the properties of the dark energy. If Einstein was right, it should sit along this line, somewhere along this line at the bottom. And what you can see here is that with Lucas's fancy statistics using machine learning, then we can confine the possible values of this of the properties of dark energy and the density of the universe to this much smaller region. So we have a much better idea of the properties of dark energy by using machine learning techniques rather than using the traditional statistics that people tend to use for analyzing these data. So machine learning and AI is definitely giving us a leg up, and we can get more information out of the data. I should probably wrap up. So let me just finish by saying what we know at the moment, or what we've discovered so far using techniques like this, and say briefly what the future is going to be. So these are results using the bending of light from this just sort of general distortion due to the stuff in the universe. So these are maps here taken with the kilodegree survey, which is based on a relatively small telescope in Chile. These are the maps of the distribution of mass, and this is what we're finding so far. So this is encompasses what we know about the density of the universe and the clumpiness of the universe from two different experiments. So the red bit here, which is the very precise measurements that we get from the Planck microwave background data, and this long banana here is what the current lensing surveys are giving us. And what you see here is that these two agree that if the true universe is somewhere inside the red circle, it will be consistent with the microwave background measurements and also these lensing measurements. If I'd been giving this talk 2 months ago, these would not have agreed. But the latest version of the kilodegree survey, which is the final one, they've moved into agreement. So that was quite a surprise, because the previous analyses of this, not this data set, because the data set has increased over time, but the earlier versions showed some disagreement. So we really thought that there was something interesting was happening in the universe. But the latest version is and final version shows agreement. And the way that these things are done these days is that the people who are doing the analysis use a so-called blinding technique. So they're presented with 3 sets of data, only one of which is the true universe. So they'll get 3 different answers, and they don't know which one corresponds to the real data until they've done it. So they had 3 so they couldn't be influenced by the red dot knowing where it should be. So what this is telling us is that Einstein seems to have been right. his gravity law fits. Einstein's cosmological constant fits. We'll be able to do this experiment much better with the Euclid satellite, which is observing as we speak. It's going to give Hubble Space Telescope quality images, but over that a third of the sky. And it's already showing some interesting gravitational lensing effects which were not seen before. So at the center of this galaxy here, there is a highly distorted thing called almost an Einstein ring, where this is just a single object whose light has been bent round into a circle like this. So we will shortly be analysing these data, and we'll be able to make a much more precise test of Einstein's theories in due course. But everything at the moment, the far future, is that it looks like the universe is going to expand at an ever-increasing rate and just get colder and colder and colder, and everything will end up in black holes and photons. So on that optimistic note, I shall stop.
Interesting. At the beginning, you mentioned about Penzer and Walker making their findings. Did the other group actually carry on?
Yes, they did. Yep, and in fact, one of the later experiments, one that I didn't talk about, between Kobe and Planck, there's a telescope called WMAP, and the W is Wilkinson. That's one of the four. Yes, no, I mean that sort of started a completely new line of research, and the culmination of which was really the Planck satellite. So there were experiments, balloon-borne experiments, ground-based experiments. Their original one was, I think, on the roof of the building in Princeton, I think. But then they went to balloons, and then to satellites, and there are also ground-based ones. So we're involved with a big ground-based experiment called the Simons Observatory, which will push things to even smaller scales than Planck was able to measure. So it really opened up precision cosmology. Before that, as I say, we knew things to within a factor of 2. It was a very rough subject, and then this has allowed us to really, get a very precise understanding of what the contents of the universe, what the properties of the contents of the universe are. What the actual contents are, we don't know, but we know quite a lot about their properties.
Thank you very much.
Any other questions? Yes.
Why is it that the cosmologists seem to be so against the concept of a negative gravity?
I don't know if we are, in a sense that Einstein's cosmological constant, in a sense, is a negative gravity. It says if there's no matter there, then things will move apart. So I think, probably there was some reluctance, partly perhaps because it was put in to solve a problem that wasn't really there, or at least wasn't thought to be there. But also, it was a very bad solution to that problem as well. In fact, that was not one of Einstein's better ideas, because it doesn't even solve. You can't even get a static universe because the universe is unstable. So Einstein's universe with lambda in it, it sort of sets up this perfect balance between the ordinary gravity pulling things in and this repulsive gravity balancing things out. But it's unstable. If you add in a little clump, then, as I mentioned before, it's going to collapse. So it wasn't a great solution, and I think. Also, the theory is just a little bit uglier, and I think it's we tend to have this prejudice that if the theory is nice and simple, we describe it as elegant, and adding in extra bells and whistles, we'd rather not do that unless it's absolutely necessary. So that's probably why. But the way that science works is that your prejudices can get overruled by data. So if the evidence builds up, then you accept it, and I think that's what's happened.
There was Alan Guth's idea that in the early femtoseconds of the universe, there was a very rapid expansion.
Yep.
Of course.
Yep. Exactly.
But that's completely unaccounted for. But a negative gravity of, supposing your dark matter attracts baryonic matter, but is mutually repellent, that will give it to you.
So, I think if you look in detail, I mean, you have to look at the observational consequences of any idea, and I think that probably doesn't work. But it's it's a good example of how science works. You make a proposal for for what the laws are, and then work out the consequences, do the experiment, and see if it agrees. I mean, Guth's idea of inflation, we still, although it's difficult to get very direct measurements, we do have some measurements that we've made that and you can ask the question: is that consistent with this inflationary period in the early universe? It's very similar to what's going on now, but at a very different energy scale. So Guth's idea would be a cosmological equivalent to a cosmological constant in the very early universe, but a much bigger one that set everything going. I mean, you can, in a sense, you can think of this as being, this is the Big Bang itself. The rapid expansion of the early universe. So that's a theory which we actually do think is probably responsible for the early phases of the universe. We have evidence that's consistent with it, but it's very difficult to get definitive proof of that.
Yeah, I'll just really comment. I don't really see that the cosmological constant was a fudge add-on. I just see it as a normal thing in the equations of having an arbitrary constant of integration, because essentially you take the stress energy tensor, right, and its covariant derivative is 0.
Yep.
You construct a tensor from the Riemann tensor in such a way with the Bianchi identities to get another tensor that its covariant derivative is 0, and because they both equal 0, you can now make them equal. Yep. Right? That's why you do it. And because the covariant derivative of the metric tensor is 0, you've just forgotten to put that in at the first place. So I don't. It was such a natural thing. It's just like you because you're trying to. You've got an arbitrary sort of axiom to make those two tensors equal, right? By a bit of a guesswork, really, right? Because of the acceleration of the separation vectors of the things.
Right.
So I just see that it was just an obvious, constant of integration to add in.
Yep.
That's
Yes, you're absolutely spot on. Yes, if you formulate the GR that way, you're absolutely right. It comes.
How it's formed. Because that's what the axiom is of making these three things, and if you have to work hard to get this tensor that has the same property that still has the same curvature, because it's a fourth order tensor, you've got to knock down to a second order tensor.
That's exactly how I teach GR to my students.
Yeah.
So, no, you're right, and there's a theorem called Lovelock's theorem that says that the most general theory of relativity that is second order and has various properties that seem reasonable has two arbitrary constants in it. One is g, the gravitational constant, and the other one is lambda. So it does arise quite naturally. It really just depends on the way that you think about it, and I like the way you think about it because that's how I think about it too. Yeah.
Any other questions from within the room? Okay, do we have any online? No? Okay. It strikes me that if Einstein had accepted the results of his initial calculations, and that the universe was not static. And he'd followed that through, and he would surely have thought about what happens when you go back in time and items were closer together, and then it follows that he would have come up with the concept of what today we call the Big Bang, which is actually a name derived by Fred Hoyle sarcastically, because he didn't believe it. But Einstein could have been there right from the beginning.
He could, yes.
Yeah.
Yes, he would have been famous.
Yeah.
Yes.
Well, for a subject that is really quite highly mathematical and quite complex, to have it explained so clearly and with entertainment as well, I think you'd all like to show your appreciation to Alan.
Thank you.
So thank you very much indeed for all of you for coming along and making tonight such a good evening. Thank you to everybody there on Zoom. Lovely to see you here again. All I need to do now is wish you all a very safe journey home, and we look forward to seeing you next time. Thank you.